Hey, what's going on, guys? Kamegigi here. So I've been working on a 6502 processor simulator, and the last several videos I've been live coding the most essential instructions for it. So currently I have LDA, LDX, and LDY, and SDA, SDX, and SDY instructions being implemented for all the addressing modes, which was a tough thing to do in terms of the amount of work being involved. And now finally I have a chance to demonstrate how the I/O, also known as input and output, is working. How did I connect this kind of features. So from now on, what I am actually capable of doing is to using the bare 6502 instructions, machine codes encoded, instructions encoded into 6502 machine codes. Using these instructions, I can do two most essential things that computer do. I can read from the keyboard and write the character to the screen. All right. So let's start the demonstration by an example in the debug mode, so we can see how the memory looks like before the execution, how it looks after. Then I'll demonstrate a couple of full-blown examples. So there would be a program, so we'll probably start with this one, a program that just prints a single character and jumps back to the initial instruction. Yeah, by the way, I've implemented the direct jump as well. So how it just prints A, like in the infinite loop. It's not exciting from the perspective of how it looks, but it's actually a valid 6502 program. So, and this, for me personally, this is exciting. And then we'll have a look at the so-called TELETYPE application, which what it literally does, it just takes the input from the keyboard and echoes whatever user has printed, has typed to screen. And you can use enter to go to the new line and backspace to erase the character that you just typed. So not very exciting, but again, like bear in mind the amount of work that I need to do in order to achieve this. Might bring a bit of a weight to this project already. Okay, so let's actually run the code. So here, just a few notes on the variables. So I have, so the way it works, in order to get the user input, all I need to do is just to load the data from a specific memory address. And oh my god, let me just try to find where did I encode that. Yeah, here it is. So in order to execute an equivalent of the get char in C, let's say, or like move 00 to AH and then call the interrupt 16 for x86 real mode. So all I need to do in 6502 assembly currently is to read the data from the address E200s. So starting from E000, I have the simulated memory for 6502 being involved. So here is where the simulated memory starts. Okay, and within this memory, I just randomly picked this this kind of numbers. They probably would be changed if one day I will go for it, sort of a compatibility with some sort of existing hardware and software reading for the hardware. Probably this would be the different addresses, but for now they just work as a placeholders. And again, like in order to, so all we need to do in order to read a single character from the keyboard within the simulator is to load the data from this specific address. And it's another interesting thing that it doesn't really matter whether we're reading this data to the A register, to X register, or to Y register. So this all gonna be working the same. Well, this is very simplified thing, and even on Apple One, it kind of works a little bit more complicated. So there is a bit that is responsible to answer the question whether the display device is ready to output the character or not. But I'm currently I've been forced to start learning the very basics of electronics, because otherwise it doesn't really seem to be possible to implement all of this hardware related stuff. Well, the processor implementation is rather trivial, but when it comes to bundling the processor together with the rest of like the monitor, the keyboard, all this stuff, and handle synchronizing all this then it really gets complicated. And as far as for this project, I really wanted to stick to just a single processor, just to focus on the processor, and the rest of the outer world that operates on is more like a bit of a software abstraction instead of the hardware emulation. That's why I call my my project 6502 simulator and not the emulator. But anyway, so in order to read the character from the keyboard, all I need is to say either LDA and this address, or LDY or LDX, because the code to read from keyboard is bundled to the function that reads a byte from the memory. And in case if we have this specific address, in this case we just read this, right? And in order to output the same thing, but we need to store the value to this to this exact address of E201, so to output the character, and this address to read the character. I'm sorry, yeah, I said that this one for read now, this one to display the character, and this one to read the character from the keyboard. So by using the single instruction LDA and this absolute address, well, actually, from the it's kind of like absolute from the bootable environment perspective, but from the 6502 processor perspective, this is just addressed. It would be like 0 to hundreds, so it would then calculate the absolute from the x86 perspective, not from the 6502 perspective. So anyway, if we just have a look at the machine codes that are about to be executed, we have this LDA, and I'm loading 200 hexadecimal. So 6502 processor thinks that this is the offset of only 200s, and to get the actual address and the actual memory on the actual hardware I'm running this, yeah, there would be the some offset that added to this value, but that's just happening under the hood. And after this, I would have in the A register, I would have the value of whatever a user has typed into from the keyboard. And also, before actually getting to the register, first the value gets into this address, right? So first it gets to the address, and then LDA would load this data from this specific address to the A register, and then it would set the value from the A register to another address, right? And there is another handler that kind of says, like, if we're writing to the memory 0201, this means that the user wants to output the character, and that means that we need actually to flash this character to screen. So that's how it's working. So we have AD for LDA absolute addressing mode, and then the address where to read the data from. And then we have AD, which is the opcode for SDA in absolute addressing mode, and the address as an argument of where to write this character. So once we're reading the character to the memory, it automatically gets printed on the screen. So this is similar to how it works on Apple I, for instance, but it's really simplified as opposed to that computer. So let's have a look. I'm sorry for a bit too long explanations, but anyway, hopefully this gave you an idea what in particular am I doing here. So currently it actually asks me for user input, and it didn't yet and the reason why the simulator is asking me for user input is because he saw that I'm supposed to be reading from the address 0200 hexadecimal from the virtual memory perspective. And once I hit a key now, it would then store the value from of what I've just clicked to the address. Absolute address is like E200, but from the 652 memory perspective, this is address 0200 hexadecimal. So if I just hit A, for instance, so what happens here? It just so before actually reading this to the A register, which happens later, it first just writes this 61, which is the ASCII code for A register, ASCII code for A letter. So it writes this to the location of this 200 hexadecimal, and then actually the instruction LDA from this particular address gets executed, and after this the value of 61 gets into the A register, and then the next instruction, whatever we have in the A register, would then get stored to the address 0102, and it just gets stored right over in here. and eventually we have what we've done. So we've been waiting for user input here, and then once we kind of type press the key, right, then it gets flashed to the display. So I hope that's clear. And in order to make it in a loop, what I need additionally, I'll get rid of this debugging strings here. So I need only execute to avoid polluting the screen with unnecessary kind of like information. So currently, if I run the same, it just I'm sorry, did I forget to execute? Hold on a sec. Well, this is a little bit strange. I'm sorry, guys. Just something has gone horribly wrong. Oh yeah, that's because I forgot to load the program. Yeah. So yeah, obviously I need to load the program. Yeah. Now waits for user input. I type in, and all done is just the debugging string. But anyway, so this means that the execution has been completed, right? So we no longer execute in 6502 code. But if I uncomment this two lines, so what this does, so 4C means stands for the direct jump, and I'm jumping to the address of where initially the program counter is pointing to. So this again, I just randomly picked value. Well, I was trying to mimic like the 6502 JavaScript emulator adopted by Nick Morgan that has been demonstrated on this channel many times before. It's just the arbitrary number, so it might be changed later on to like be more kind of like how to call this, compatible with the real hardware and software. But anyway, it doesn't matter. So currently what this instruction does, it actually points the program counter back to the initial instruction, and then it just executes this sort of a thing in a loop. And eventually what we have here, we have this TELETYPE application. So I can just type, I can erase. That's pretty much all about it. So whatever string. So this this program runs using only 3 6502 processors instructions, and the instructions are LDA. Let's make it like LDA from the address 0 to 00, then STA to address 0201, and then jump to the address of 600. And that's pretty much all about it, right? So what is cool about this, that this is the proof of concept. This is the proof of concept implementation of the bare minimum I/O handling, basically. Again, like not the emulated but simulated, because it's really simplified. But anyway, so the cool thing that actually this program works. This app has been programmed entirely in 6502 machine codes. Now, I just want to demonstrate another little application. So, for instance, we consider another program. So let's load the value of 61 to the A register, right? And just to give you an idea of how that works, if I just bring the debug info before executing, actually I can do this after execution, right? Where is that? Call print debug info here. I think this is enough, right? So what happens now? So I just load the value of 61, the constant immediate data, to the A register, right? And then what I do next, I print this to screen using the STA and to this exact address where we've been writing already in the previous program. So AD is the opcode for STA in the absolute addressing mode, and here is the address where we're supposed to be writing. So this is the display variable, right? So I didn't use the variables here just to operate on the real addresses for now, but I could have used the display variable here as well. So this is what happens, and because of the fact that it actually gets stored exactly to this kind of place in the memory, it actually gets printed to screen as well. But obviously also this actually if I just bring the memory range again, this should be there as well. So yeah, here it is. So it just prints the character, and here is the memory range for this. So the address of E to 01. So here it is. We have the value of 61, right? So that's where we've printed the value to, right? So probably just to give this a little bit more sense, I could have printed debugging information. Well, actually, just this should be, yeah. So, and if I just print, if I print the same thing, but before, right, before the execution. So before the execution, we have nothing in the memory, the simulated memory, and we have nothing in the A register. But after, we have this value. Well, actually, it's better to say, just swap them a little bit. Let's put them like this. Just would be a little bit more instructive. Yeah. So now, after executing this, so it executes first instruction. It executes LDA the immediate data of 61. So we're getting the 61 into the A register. Then he executes STA to 0201, and here it goes, right? So, and if it goes here, it also prints the character on the screen. So that's pretty much all about it. Now, if we just get rid of no, not this one. If we just get rid of all the debugging stuff again and enable the loop. Now this time things are going to be a bit more interesting. So we just add in the loop. So it would it won't be doing this once anymore. It would be doing this in an infinite loop. So it would be doing this, printing this A character. So loading 61 to A, and then just print. And by the way, we can even step to, not here, I will demonstrate you this just right at the moment. So this version reinitializes the value in the A register, but actually it's not even needed. We can even say like this, I believe. So we jump not to the very first instruction to set the value of 61, set the A register to the value of 61, but instead we can go strictly to this one, where it already says the value of the A register. So as far as the value of the A register has already been set here, it should be working as well. So it would be just output and jump back to output, jump back output, and that's pretty much all about it. So the same output, right? However, if I just try to jump to, say, so this is going to be 2, 3, 4, 5, 6. So it would be jumping to where the jump is. It would just stuck forever. It's not going to be doing anything. Hold on a sec. Oh, it just sorry, I've jumped to the wrong instructions. So I've jumped to the 06. Let me think. Well, let's just jump to. Okay, so 1, 2, 3, 4, 5. Sorry guys, I'm not sure where exactly should I jump. No, it actually doesn't go. I just want to stuck this in the infinite loop. Oh, what have I done? It's not supported. I'm just missing. 2 is not supported. Okay. 4, 5. Okay, this is what I wanted to achieve. So now you see, like we just typed this letter once, and then we stuck because we're jumping to where we currently are, right? So just jump into like it's called the processor trap, for instance. So it just jumps from where the jump instruction is back to this exactly the same jump instruction. So it just kind of stacks forever in the infinite loop, but not actually doing anything here, right? So this is pretty much all about it. And yeah, and if we jump somewhere to like further on where we have no program more, it would then escape from the loop because the next instruction, because the instruction where we jump is 0 0, and it just made the way that if it encounters the 0 0, it just stops executing. So here we just so that's all done, tells us that we actually escape from the program loop completely. All right, so well, this is pretty much all about it basically, guys. So let's just drop it back to printing a forever, right? And probably the very last thing to demonstrate in this video how actually this I/O handling is implemented within the code. Again, not the most ever exciting thing really, but let's have a look. So if we go to get ABS absolute value, right, this is the implementation. So it just performs the regular routine to get the memory from to get the value from the memory up until here, and he asks, so are we reading the so if AX AX currently stores the address to read from. So if this address is equal to keyboard, which is from in the absolute memory, this is E200. In the simulated memory, this is 0200. So if we have this address, right, in this case, we want to get the character, right? So jump into the get character. Here, we're actually using the bias interrupt to get this character, so simulating the hardware sort of a thing. And then we point in SI to keyboard, and we're writing whatever we got in AL after user pressed the key to this exact memory address. And then it jumps here, and then we just load the data from, it's not from the 0 page, it's from the memory address, yeah, as well as here, because this is not the 0 page anymore, right? Yeah, so first we just read this, then we store it to where the keyboard variable is, then we just load in the single byte from there. And that's how we got our A register being initialized. So I know this is probably the worst possible implementation, and again, like the way how it works on the real deal is way more complicated, but it does what I wanted to do. So for now, I'll probably leave it as is, for it just feels like fairly enough for me. And now the very last thing to consider, we just have a look at the set absolute value, or set mem value, yes, set memory value. So here, here the similar thing is happening. So we're comparing SI with the display, which is 0 to 01, right? Address, and if it is that we know that user is supposed to be writing the character, just echoing the character to the screen. So we go into here to put char. So here we're calling this bias code to output the character. So we're using the bias interrupt here to write the character again, like, and also we do put this. We actually get in the so in order to know which character in particular do we want to write to the screen, we're getting this from the memory, so we already stored it there, right? So first we store this to the memory, right? And then if it's about to be displayed, if this is the address that we're looking for, it would get displayed. So we're fetching the value of the character to print from the memory, and then we just bring this to screen. And we just handling things like if we have if a new line is pressed, that we're adding like a part of a character return. We also add the new line character, and also I'm setting the attribute here as well. Okay, guys, so this is pretty much all about it. So as you can see that the x86 bias interrupts to read the keystroke from a keyboard and to echo the character to the screen are made in the way so that So they do interact using this 6502 simulated memory addresses, the specific addresses that provide the access to this x86 interrupts. So from the 6502 environment perspective, we're just reading the data from the specific address to force the user input interrupt, right? And in order to force the echoing the character interrupt, we just write into the specific memory address, and that's how we're getting our I/O or input-output handling being done and working. Okay, guys, this is it from my side. So from now on, I can keep implementing the rest of instructions to not only to read and write the data from the memory, and not only reading the data from the memory, not only writing the data to the memory, but also making some calculations actually, so to be able to actually run some real 6502 programs on this 6502 processor simulator. But again, like now we're able to communicate with the outer world in a bit weird way, but still it works as a proof of concept. So I'm quite satisfied with this, with what I got so far. So yeah, this is it from my side. Thanks for watching. Until the next time, and take care.